Imagine you walk into a small room with only 23 people. Not a stadium, not a school, just 23 people. Now here is the question. What is the chance that at least 2 people in this room share the same birthday? Most people feel the answer should be small. There are 365 possible birthdays and only 23 people. So 50% sounds impossible. But the real answer is slightly above 50%. And the reason is one of the most beautiful traps in probability. This is not just a party trick. Think about a classroom with 30 students, a company meeting with 25 employees, a wedding table, a small conference room, or even a computer system assigning random ID to users. In all of these situations, the same hidden question appears. How many things do we need before 2 of them collide? Birthdays are just the easiest version to see, but the deeper idea is collision. The first mistake is that we compare 23 with 365. We think 23 is much smaller, so a match should be rare. But that is answering the wrong question. Your brain often asks, what is the chance that someone matches my birthday? If your birthday is fixed, each other person has only a 1 out of 365 chance to match you. With 22 other people, that probability is still not close to 50%. But the birthday paradox is not asking whether someone matches you. It asks whether any 2 people match each other. Now change the question. Instead of checking who matches you, we check every possible pair in the room. Person 1 can match person 2. Person 1 can match person 3. Person 2 can match person 3. And this continues across the whole room. With 23 people, there are not 22 comparisons. There are 253 different pairs. That means the event gets 253 chances to happen. So why not just count the chance of a match directly? Because at least one match can happen in many different ways. Maybe exactly 2 people share a birthday. Maybe 2 separate pairs share 2 different birthdays. Maybe 3 people all share the same birthday. Maybe several collisions happen at once. So probability gives us a cleaner trick. When an event is hard to count directly, count the opposite event first. The opposite of at least one shared birthday is very simple. Everyone has a different birthday. There is no collision anywhere. These 2 events cover all possibilities. Either at least one match happens or no match happens. So the probabilities must add up to 1. Now count the probability that nobody shares a birthday. The first person can have any birthday. So they have 365 safe choices out of 365. The second person must avoid the first person's birthday. So 364 safe out of 365. The third person must avoid the first 2. So 363 out of 365. The fourth person has 362 safe choices. Every new person has 1 fewer safe day available. So for n people, it is a product. For the birthday paradox, we use n equals 23. So the no-match probability becomes 365 over 365 times 364 over 365 times 363 over 365, and so on until the 23rd person. The 23rd person must avoid the birthdays of the previous 22 people. So they have 343 safe days left. When we multiply all of these terms, we get about 0, 4,927. Now we flip the probability back. If the chance that nobody shares a birthday is 49, 27%, then the chance that at least 2 people do share a birthday is 1 minus 0, 4,927. That gives 0, 5,073, or about 50, 73%. So in a room of only 23 people, a shared birthday is more likely than not. Now the result becomes much easier to believe in real life. In a class of 30 students, the chance is about 76%. In a room of 40, about 89, 1%. With 50, about 97%. So if 2 people in your class share a birthday, that is not a rare coincidence. Mathematically, it is expected. The curve rises quickly because the number of pairs grows quadratically. When you add 1 person, that person compares with everyone already in the room. So each new person adds more and more pairs. Our brain sees 23 people, but the math sees 253 comparisons. This idea is not limited to birthdays. In computer science, it appears in hash collisions. A hash maps an input to one of many outputs. If two different inputs produce the same output, that is a collision. The birthday paradox tells us collisions appear much earlier than intuition expects. The exact formula is the birthday product in general form. It is approximately 1 minus e to the negative n times n minus 1 over 2m. With m equal to 365 and n equal to 23, this gives about 0. 50. Finally, we can see the formula through simulation. Create many rooms. Each room has 23 people. Assign each a random birthday. If at least 2 people land on the same day, mark that room gold. If all birthdays are different, mark it gray. After many rooms, the percentage of gold rooms settles near 7%. The formula and the experiment meet at the same answer. The birthday paradox is not really about birthdays. It is about hidden comparisons. One pair sharing a birthday is unlikely, but 253 pairs create many opportunities. Probability is not only about how rare one event is, it is also about how many chances the world gives that event to happen. If you enjoyed seeing the math beneath the surface, subscribe. A new visual proof every week. Thanks for watching. See you in the next one.